Hello, this is chapter 3.2. We're still on the topic of acids and bases, and we're looking at an introduction to organic reactions and their mechanisms. This lecture will be delivered over 5 videos. The first 4 videos look at the different features of structure-acidity relationships in a hierarchical fashion, which can be used to rationalize the strength or weakness of an organic acid or base. These make up the acronym CARIO, C-A-R-I-O. The last video is a short video concerning acidic protons and their chemical shift in proton NMR spectroscopy. In the previous lecture, we only really looked at using pKa values to determine the likelihood of an acid-base reaction without really understanding the intrinsic structural features. This time round, we're going to look at those intrinsic structural features of a molecule which allow it to behave as either an acid or as a base. One thing that is common to this video is the following message, that when we see a low pKa value, we can assume that the dissociation of this acid or the conjugate acid will lead to a stabilized anion. This is an ion with a negative charge. There are 5 factors that need to be considered when thinking about the acidity or basicity of a molecule and using pKa values, and we're going to survey each one. The first factor that we need to consider is the atom that is neighbouring our proton. Once the proton is gone, then the electrons are going to be left on that neighbouring atom. So we'll need to think about that atom's charge, its electronegativity, and its size, because these will all be factors in determining how well they're able to either bear that negative charge or disperse that negative charge over a volume. Now, a charged species will always be more unstable than a neutral species. Since an acid becomes more negative upon the loss of its proton or protons, the stability of the new lone pair on the conjugate base is a key factor in determining how favourable the dissociation reaction will be. The lower the charge density on an atom, the more stable that species is. So the stability for these reactions goes in the order of the least stable, which is the oxygen dianion, to the most stable, which is our neutral water molecule. In terms of deciding the strongest acid then, the hydronium ion is the strongest acid because on reaction with water it forms the neutral molecule water, which is the most stable of these conjugate bases. The weakest acid is the hydroxide ion because on reaction with water this will form the oxygen dianion, which is incredibly unstable. So therefore the hydroxide, being the weakest acid, will make this the strongest base of these 3. The next thing we're going to do is tie this in with the pKa values and also compare this trend with nitrogen, which is to the left of oxygen on the periodic table. Although the charge distributions on an oxygen and nitrogen atom are different, they demonstrate the same trend in pKa with respect to increasing the positive charge on their atoms. That is, they become more acidic, and this is reflected by the decrease in pKa across this series. The removal of a proton from either the hydronium or ammonium ion is easiest because this decreases the formal charge by 1 unit and forms a neutral molecule, that's water or ammonia respectively, as the conjugate base. This of course is easiest to do when the atom bears a formal charge of +1 in the first place, but this becomes progressively more difficult as the overall charge of the conjugate base becomes negative, i.e. as we move towards the left. When this happens, conjugate bases become destabilized and are more likely to accept a proton to try to become neutral again. In other words, they start to behave as a base. The next thing that we're going to consider is the electronegativity of the atom to which the proton is bonded to and how readily this will dissociate. Here are some second row elements and their acidic compounds. As the electronegativity increases of that second row element from left to right, the pKa decreases. And this is as expected, because the higher the electronegativity of the atom, the easier it will be for that atom's conjugate base to acquire a negative charge, and thus be stabilized. Thus the acidity increases from the left to the right of the periodic table. Conversely, the basicity increases from the right to the left, and this is because, again, of electronegativity. The carbon is far less electronegative than the fluorine atom is, and so therefore it is a far stronger base, because the lone pair on the methanoid ion is going to be much more destabilized than the lone pair on the fluoride anion. Now, to come back to talking about acidity, hydrofluoric acid is a weak acid, and this we need to consider another factor. Let's have a look now at the electronegativities of these atoms as we descend group 7. The point of hydrogen fluoride being a weak acid causes a lot of confusion due to the presence of two seemingly conflicting trends. Here's the first point. We said that acidity increases as we go across a row in a periodic table. That makes sense, right? It makes sense that the fluorine atom is more electronegative than the oxygen atom, than the nitrogen atom, and then the carbon atom, because of the greater electronegativity of fluorine versus those atoms. And a fluorine bearing a negative charge is a happy fluorine. But here's the seemingly strange thing. HF, we said, is not a strong acid. Not in the sense that it completely ionizes in water. Now, hydrofluoric acid is a weaker acid than hydrochloric acid, hydrobromic acid, and hydroiodic acid. So what's going on here? This is why considering the atom first in determining the strength of an acid or base is so important. You can make two arguments for why this is. The first has everything to do with the shorter and stronger hydrogen-fluorine bond as compared to the larger hydrogen halides. The second then has to do with the stability of the conjugate base that's formed and how it stabilizes its negative charge. The fluoride anion is a tiny anion with a really small ionic radius of any other anion bearing the same single negative charge. Its charge is therefore spread over a much smaller volume than that of larger halides. High charge densities tend to be less stable than low charge densities. The more spread out a charge can be, the more stable it will be. So, as we go down the periodic table from fluoride to iodide anions, notice that the magnitude of the negative charge doesn't change, but the volume that it occupies does. Iodide ions being considerably larger than fluoride ions, so 206 picometers versus 119 picometers, means that the iodide ion is far more stable, and that hydrogen iodide or hydroiodic acid is a stronger acid than hydrofluoric acid, and this trend holds true for atoms in other groups. We can observe the same pattern for the group 6 elements and their acidic compounds. So as we go down the group, we can see that the pKa values are decreasing, and this is reflecting the decrease in bond strength between the acidic proton and the group 6 element. The anion, however, for those elements, that's sulfur and selenide, form fairly readily once a proton dissociates. So the inverse can also be argued when we're thinking about base strength. When the pKa is increasing up a group or towards the left of a period, then the conjugate base is destabilized. And this correlates with either the volume becoming smaller as you ascend the group for that ion, or if you're going towards the left of the periodic table, then the electronegativity effect dominates because the electronegativity is less, and the conjugate base of this atom is destabilized because of its inability to hold the negative charge. Think of methanoid. as being the strongest base as evidenced by its pKa value.
This concludes part A.
In this video we're going to have a look at the effect of resonance and how this affects a pKa of an acidic substance. Now resonance is another means by which a negative charge can be dispersed in a molecule. If the conjugate base has a charge which can interact with adjacent double bonds or p orbitals, its stability can increase, and this leads to an increased acidity of a conjugate acid. This becomes especially useful when trying to judge which is the most acidic proton when it's bonded to the same atom. In this case we're going to look at oxygen and consider two examples. In the first example, ethanol has a very high pKa because the oxygen anion of the conjugate base cannot disperse that negative charge. The map of electrostatic potential shows this because the red area represents the high electron density, and it's all localized on that oxygen atom because it's the most electronegative atom. However, when we consider acetic acid, its pKa is considerably lower, so therefore it's much more acidic. In fact, it's 10 to the power of 12.25 times more acidic than ethanol. Now this proton is also connected to an oxygen atom. However, the oxygen atom in this case can disperse or delocalize the negative charge over the two oxygen atoms, and this is shown by the two resonance forms. The carbon-oxygen bonds in the resonance hybrid are now of the same length, and it's possible to see, using the map of electrostatic potential, that the electron density is distributed over the two oxygen atoms. By delocalizing the charge over these two atoms, this makes the conjugate base acetate far more stable than the corresponding ethoxide anion. Let's have a look at another example. In this example, we have a proton connected to oxygen again. The only difference is the ring to which they're connected. The ring on the left is a cyclohexane ring, and the ring on the right is a benzene ring. The pKa value of the proton of cyclohexanol on the left is 1,000,000 times less acidic than that of phenol. Again, the answer is down to resonance stabilization of the conjugate base. On the right, we see an energy profile for the deprotonation of these acids. From this diagram, it should be clear that less energy is required for the dissociation of phenol, and this is because of its resonance stabilization. Phenol already has some resonance stabilization by being able to donate the electrons of the lone pair of oxygen into the benzene ring. However, once the phenolate anion is formed by the loss of the proton of phenol, then that negative charge is shared over 4 atoms rather than 3.
This concludes part B.
In this video we're going to look at the I of Careo, which is the inductive effects. In our first example here, all of the bonds are non-polar, and so none of the protons in ethane can really be considered as acidic. However, if you have a molecule that contains polar bonds, then the pull on the electron density from the electronegative fluorine is transmitted throughout the bonds by long-range effects. Therefore, the electron density of the carbon-hydrogen bonds, or the carbon protons, and the bond strength of the C1 proton bonds are lower than the bond strength of the C2 proton bonds. This is why the partial charge is smaller on C2 than it is on C1. Inductive effects can be stabilizing in terms of the conjugate base, so we call these negative inductive effects, or they can be destabilizing. In other words, they can be positive inductive effects. If a proton was lost from C1, then the negative charge on that carbon would be more stabilized than if any of the protons on carbon 2 were removed due to this inductive effect. Let's take a look at this in a little more detail now. On this slide we have acetic acid, that's compound 1, and from its map of electrostatic potential, the oxygen atom of the carbonyl group is the most electron rich. That means the charge is heavily localized on that particular atom. Now when it forms a conjugate base, the negative charge is stabilized by resonance, which means that the electron density will be shared over the two oxygen atoms. However, we can see that substituting a hydrogen atom at the other end of the acetic acid molecule for increasingly electronegative substituents, that's bromine in molecule 2, chlorine in molecule 3, and fluorine in molecule 4, causes the pKa to decrease. Yet, look at the placement of these electronegative atoms. They are 3 bonds distance from the acidic proton. Each carboxylic acid forms a conjugate base, that's the carboxylate anion, with the same number of resonance forms, that's 2 for each molecule. So it's not possible to rationalize this increased acidity based on resonance arguments. Therefore, this added stabilization is caused by a long-range effect, the inductive effect. This is also evidenced by the decrease in that red region surrounding the carbonyl oxygen group. That means that the electron density is being removed from that. Let's look at fluoroacetic acid, which has the lowest pKa value. Fluorine has the highest electronegativity, and so therefore has the strongest pull on the electron density for the neighbouring bonds. Consequently, fluorine shows as the most electron rich, but also we can see that the red region is more spread out on that carbonyl oxygen, looking at the map of electrostatic potential. When the proton of fluoroacetic acid is removed, the fluorine atom helps to further spread out the electron density of the conjugate base, which, as we know, has a stabilizing effect. On the next slide, we see a table of all of the electron withdrawing groups and donating groups that can either stabilize or destabilize the conjugate base respectively. This slide contains a summary of the electron withdrawing groups and the electron donating groups. So any atoms or groups of atoms that are electron withdrawing, that is, remove electron density away from the carboxylic acid group, weaken the bond between the acidic proton and the oxygen, and this is a negative inductive effect as it stabilizes the conjugate base. Atoms that are capable of donating electron density towards the carboxylic acid group strengthen the bond between the acidic proton and oxygen, making the proton less likely to dissociate. Therefore, should the conjugate base form, it would be more destabilized, we can even say more basic. How else can these inductive effects manifest themselves within a series of molecules? Let's take a look. In acetic acid, which is our benchmark, when all of the protons neighbouring the carboxylic acid group have been replaced by fluorine, the pKa value reduced by 4.53 units. This change makes trifluoroacetic acid nearly 339,000 times more acidic than acetic acid. In addition, when we look at the conjugate bases of these acids, the red area corresponds to electron density, and it's much lighter in trifluoroacetate than in the acetate anion. This is because the inductive effect delocalizes the charge in trifluoroacetate more effectively than in the corresponding acetate conjugate base. Let's now take a look at the effect of increasing the number of electronegative atoms or electron withdrawing groups in a stepwise fashion by replacing each hydrogen atom of acetic acid with chlorine and measuring its pKa. Note that in any comparison, we must only change one thing at a time. In this comparison, we keep the carbon chain and the type of halogen the same. The only thing that is changing is the number of electron withdrawing groups with each successive acetic acid molecule. So it is clear to see from the decrease in pKa over the series of substituted acetic acid molecules that the effect that this has is to stabilize the conjugate bases of these acids. There is only one factor left to consider for the inductive effect. Let's look at this now. We've come full circle here. If you remember at the start of the video, we talked about the transmission of the inductive effect over a varying bond distance. In this case, we have molecules that contain the same number of carbons, that's 4, and the same type of electronegative atom, that's chlorine, but the position of the electron withdrawing group is decreasing with respect to our acidic proton. When this happens, there is a corresponding decrease in pKa. This means that the inductive effect is magnified the closer to the acidic group it is. So when these acids are being deprotonated, the most stable anion is the one that has the chlorine atom closest to the carboxylate group. So far, all of the conversations have been concerned with the electron withdrawing groups. What about the effect of electron donating groups on acidity? On this slide we see the result of positive inductive effects and their consequences for the acidity of an alcohol series. Now the point here is that the alkyl groups behave as electron donating groups. So when there are more of them placed around the acidic group, which in this case is the alcohol, then these protons become less acidic. If anything, losing a proton, say from tert-butyl alcohol, which has the highest pKa in this series, would result in the most destabilized alkoxide, as all of the electron density is being pushed onto the oxygen atom. This would correspond to the most basic alkoxide in this series.
This concludes part C.
In this video, we're going to look at orbitals and their hybridization and the effect that this has on pKa values. Now, in the last video, had we not been able to determine the acidity of a structure based on an atom's charge or its electronegativity, ability to form resonance structures, or any of the inductive effects, then it's this last factor that can be used to make a distinction between two organic molecules and their relative acidity or basicity. The orbitals that make up these hydrocarbons can be used to determine the acidity of the hydrogens that are attached, which by the way aren't particularly acidic. When making comparisons, we're keeping everything the same. That's the atom to which our acidic proton is attached, and the null possibility of any resonance or inductive effects. The only thing that changes is the hybridization of the atom to which the proton is attached. We can see that with increasing S character that the pKa decreases and that this increases the stability of the conjugate base or the anion. And this is akin to the effect of electronegativity. The more S character in the orbital, the closer the electrons will be to the nucleus and the lower in energy, or the more stable they are.
This concludes part D.
And in this video, we're going to look at the proton NMR of carboxylic acids. On this slide, we see a range of chemical shifts for a number of functional groups, and in particular, all of the broad peaks or signals for hydrogen bonded oxygen and nitrogen atoms. In particular, we're going to pay attention to the carboxylic acid group, which is highly deshielded and is the most downfield of all of our NMR signals. This can appear from a chemical shift range between 9.5 up to 13 parts per million. Now this is because of the electron withdrawing nature of the carboxylate group and the anisotropic effect of the neighbouring carbonyl bond. Let's take a look now at the proton NMR for a carboxylic acid. Just as it was possible to quench, that is to remove the OH and NH signal using deuterated water, the same is true for carboxylic acid protons. As expected, peak D would disappear when dissolved in a deuterium donating solvent. Unfortunately, carboxylic acids are often insoluble in these sorts of solvents, such as deuterated chloroform, so sometimes a piece of sodium has to be added, which removes the proton to make a sodium salt, which is then soluble in the deuterated solvent. This concludes chapter 3.2.